Hi folks, I'm Prof. Joe. I'm a professor for automation and measurement technology at the University of Applied Sciences in Kempten in the very south of Bavaria. This is part of my lecture series on measurement technology, which is AI tutored, meaning AI will give you and teach you all the content, and these videos are only meant to give you some more focus, to give you some extended information and to explain the things around the really important stuff on the content. This part is about measurement results and explicitly the statistical calculus of regression, the regression calculus. So what is that all about? It always sounds awesome, to say regression calculus. That sounds great, but it also sounds a little bit scary because most of the time people don't really know what it is all about. So just let's give a simple example of what we are aiming to do right now. It's just imagine we have the voltage and the current of a given resistor R. Now, we all know increasing the current will increase the voltage, and that should be quite linear in the end, while the steepness, the gradient, gives us the resistance R. And that's all about regression calculus. Now imagine doing more measurements. We will see that all those measurements will somehow lay around that line. That optimal linear behavior between the voltage and the current won't be as perfect as it is given by the mathematical equation in reality. Meaning that we get little deviations of our single measurements from that optimal linear line. Okay, and now linear regression is the way of finding that red linear line as an optimal line, meaning as a line which reduces the sum of all the errors of the single measurements. Again, it's somewhat the same thing as the standard deviation for a mean value, but now we have two measurements which are connected in a formula. Let's see how we could solve that problem. It's as easy as I told you. We have some given facts. We know, first thing, we know our quantity y, which is u over here, is given as the gradient times the x value plus some errors, the blue errors. In this respect, that's u equals r times I. Okay, and now we want to find m, n, an offset, and want to get some idea of that error. That error, is nothing more than the single errors of each measurement summed up. But let's get some more deeper into the mathematical facts so we get a better idea of what we need to do to solve that problem. Okay, so the problem itself is an optimization problem. To say it explicitly, it's the same problem as all the machine learning algorithms have when optimizing their networks. We have an optimization problem. What do we want to optimize? We want to optimize an error. That's explicitly the same thing all the machine learning algorithms do. They are optimizing for an error. So let's define the error. We will call our error k, and it only has two parameters we can change. It's the gradient and it's the offset of our linear relationship between y and x, or u and I in the example. So, what is the error? The blue lines over here, it's the sum over all measurements, so we need that sum. And what do we want to sum up? We want to sum up the difference of the measured value in u, which is the measured value in y. So it's the measured value in y. That's the y direction in the graph. Minus what? Minus the dot on the linear relationship itself. And that's a simple linear equation. M times the measurement in x, it's a linear relationship, plus the offset. So this part is the red line. This part are the black measurements. We built the difference of it all, and that denotes us that little error I'm marked in blue over here in the graph. Now, in the end, we are summing up over those differences, over those deviations, and square them. Why do we square them? It's the same question as I've discussed in part 1 of this chapter about the standard deviation, because it's a good thing to square it. Now, talking about machine learning, they do change the behavior, the calculation of these errors, and don't always use the squared error, but use the absolute error. We would be free to do so also, but for reasons of statistics, we are in statistics, we will use the squared error. Okay. What about this equation? It looks terrible somehow. It's really not a terrible equation, but it somehow looks unfamiliar. Why does it look unfamiliar? Because it seems to be so that we right now don't know what to do. But to be honest, we already know everything. We want to optimize this function so that the value of k gets minimal. Now, a minimum of a function. The minimum of a function, it's easy to find. We know everything about that. We just have to do some derivations of that function and set them equal to 0. In this case, we have two parameters, m and n. We derive for them and just put them equal to 0. We get two equations, an equation A and B, and we have two unknowns, m and n, so we are done. We can solve for m and n and get the optimal value for the gradient and the offset, for the gradient m and the offset n, to get the minimum of that function k, which denotes our errors. And that's the next thing. This is a good estimate for the error we denoted over here. So altogether, it seems to be a simple task to do linear regression. Now, solving that equation is not that difficult, because it's a simple set of two linear equations with two unknowns. So we know everything about that to solve it. To get a better glimpse of how that feels, how those errors are built up, one can use some graphical techniques to estimate that errors by just drawing some parallel lines which just enclose all the measurements. Now we get an estimate for our n and the errors in n. And now we'll just take the last measurement and the first measurement and draw some lines from the extremal points, and we'll get some gradient m and some error gradient m's, which give us a glimpse of the error of m itself. Now there are mathematical ways to get the errors in n and m, but we'll just take that graphical evaluation method, or that graphical glimpse of how to evaluate the errors in the gradient itself and in n. That in fact is important for the measurement itself, because when that's u and that's I, we want to give a value for r and we want to have an error in r. And now the error in r can be somehow derived from the extremal curves we painted over here. So we could use that extremal curve and that extremal curve, get the gradient, and now compare it to the given gradient of our optimal line, of our red line over here. And now the difference, the biggest difference of those three gradients could be used as a measure for the error in the gradient, or for the measure as measure for the error in R, for the example with the voltage and the current. Awesome. So overall, we now have the possibility to do some linear regression, as it is called. For example, a linear relationship between two variables. Now, everybody knows these relationships don't have to be linear. They could be exponential, polynomial, or whatsoever. But now, think about what we've done over there. It's linear regression because we used a linear relationship over here, but we could use an exponential relationship also. That exponential relationship would have 2 or 3 parameters. That depends on us, how many free parameters we want to give that system. And now we can do the same derivations, get some more complex linear equation systems, but in the end could solve them and get a nice result for any which relationship we have over here. One thing about those relationships, talking about polynomials, we could always use a higher polynomial to get the perfect match for any measurement. Imagining some measurement points at any place, we could just say, oh, we have 5 points, so let's take a polynomial of grade 4, and we would get some curve which perfectly fits through any point. But as you already see, that makes no sense. That relationship we would propose would be perfectly matching to the measurement, but would give us no insight into what real relationship those measurement points hold. So always be careful to choose the right relationship, a relationship which makes sense in respect to the measurement. Okay, finally, let's take the step towards machine learning. Now, imagine those points are pictures. So, what does that mean? Pictures, they have about 1 million pixels with a color. Each color has a value. So we have a row of 1 million colors, which we'll put in as our measurements. Now we'll use another equation than a simple linear relationship. We would use the relationship defined by a neuronal network. That is nothing more than multiplying that 1 million color vector by a big matrix, and again multiplying it by a big matrix, putting some functions around that, and so on. And that is all derived from the natural brains, from the natural brain connections. So I won't go into detail with that, but just imagine you have a vastly huge equation over here, which connects those 1 million inputs to at least 1 million free parameters, unknown parameters over here, like m and n. And now we get the same problem. We can now define an error. How can we define an error? We know the picture of an apple with its 1 million colors coming in as x values. And now we define as output a row of 8 numbers which denote the ASCII code for a text. And now that text we want for the picture of an apple or the pictures of apples would be apple denoted in ASCII text. We can put that into those equations. There's no problem about that. We can calculate and define an error. It's well defined. That error is really well defined. Just imagine that y is a vector of 8 numbers denoting ASCII text, and x is a vector of the length of 1 million colors denoting the picture. And now we do a huge calculus around that x using matrices and in form of neural networks. And in the end, we can get an error which has indeed a lot more free parameters over here, like 1 million, 2 million or more, and for which we have the same task. We want to optimize that error. So we have a lot of pictures of apples, and the outcome should be always the text of an apple. So we can sum up over all the apple pictures in that formula and get a real huge error in the end, summing up over all apple pictures we have. And now we can optimize that function for always giving us in the end the same value which is given by the word apple over here as outcome of our huge big formula with all of those parameters. And optimizing for those parameters is not that simple anymore, for sure. But in the end, it's all about optimizing the error. The same thing as we did over here. We could do it here analytically, so we can have a real solution, an exact solution for that. Having millions, billions of parameters over here, we cannot do an exact solution anymore. So we have to do some approximations, get to the point of our solution approximately. There are a lot of ways to do so, already known way before in time, now redefined by backpropagation in machine learning explicitly for those huge systems of neural networks we have nowadays. Okay, so what that means is, this is what machine learning means. The machines do not do any magic. They are just doing stupid optimization of errors. And in the end, we get some huge AIs like ChatGPT, which nowadays, at least in text form, seem to be as human as a human is when typing into a chat program. That is awesome somehow, but on the other hand, scary too, because that means what happens over here is no magic at all. It's somehow even determined. Think about mathematical equations, that's all determined. And now, taking the way back implicitly, that means everything up here is somehow determined also. That's not a bad thing, but it feels somewhat scary. You know, it doesn't change the way we feel, the way we live as humans, but it gives us some implications of what happens in our brains. Is there a free will? We cannot be sure about that anymore. Is it important to have free will? Well, from my standpoint, no. I feel great, you know. I feel great. I feel free. I learn things. I do stuff. It's awesome. Thinking about judgment. That gets complicated. Going back in time, there were some mental illness outcomes which were put into prison, meaning that when you were schizophrenic, a few hundred years ago, you would be punished, put into prison, or even be killed or tortured because people thought the devil rides your brain, rides your mind. And nowadays, for our judges, it's obvious that this person has a mental illness. Talking about that, a whole lot of stuff happens we have to think about in future, especially in the area of judgments. But on the other side, not having free will feels exactly the same way as thinking to have free will. At least for me. There was a time when I was a kid, I was sure there's something like free will, which is doing stuff up in my brain. Now I'm tending to think, no, there's no free will. But I also think, so what about? It still feels the same as back then when I was a kid. So, just go on. It's awesome. Okay, when you like that stuff, feel free to subscribe. And see you next time with Chapter 4, a short recap of electrical engineering, which we will need in the outcome of the next chapters when we go into details about errors, about voltage measurements and current measurements, which are in the very core and center of measurement technology.